Yeah, I think it is. Yeah, it is started. Go ahead, Thangavel.
So we can, so welcome to the APRG seminar. I think it's a very good idea that we are starting again the online lecture series so that we can catch more people to give talks. I think probably this is the first online seminar, and then we are happy to have Kalachand Shuin from Seoul National University. And he's going to talk about multilinear maximal averages defined on non-degenerate hypersurfaces. So, Kalachand, you can start.
Yes, thank you, sir, for the introduction, and thank you, organizers of APRG seminar, for giving me this opportunity. So, as sir said, I'll talk about multilinear maximal averages defined on non-degenerate hypersurfaces. So, we'll quickly see a few notations. So, I'll define BDX, R, denote a d-dimensional ball of radius r centered at x. Then I'll define A d lambda be a d-dimensional annulus given by this set. And then for any point y in Rd, we'll denote the usual notation mod y by this norm, L2 norm. And then the Schwartz space is defined by, it is the space of all smooth functions which has rapid decay. For example, all the compactly supported smooth functions are contained inside this space. And this Schwartz space is dense in LP for all p greater or equals to 1 less than infinity. And one non-compact support function is the Gaussian function e to the power minus mod x square is a Schwartz class function, and any polynomial multiplied with the Gaussian function is also in this space. So we'll define our averaging operator for these nice functions. So we'll first define the spherical average. So we'll consider d sigma to be the normalized surface measure on the sphere as d minus 1. Then we take supremum over all these averages. So the spherical average first appeared as solution of wave equation. And in order to study the point-wise convergence of the solutions, we need to basically study the LP boundedness of the maximal average. And that's why Stein considered this operator called a spherical maximal function, or we sometimes call it Stein's maximal function. And he proved that for dimension d greater or equals to 3, this spherical maximal function is bounded on LP if and only if p is strictly bigger than d over d minus 1. And almost 10 years later, Bourgain proved it for dimension 2. He proved that the circular maximal function is bounded on LP if and only p is strictly bigger than 2. And at the endpoints for dimension 2, even for p equals to 2, even the restricted weak type estimate does not hold. But in higher dimension for d greater or equals to 3, one can prove restricted weak type estimates for p equals to d over d minus 1. Now we'll consider similar averaging operators on different hypersurfaces. For example, so let sigma be a smooth compact hypersurface of having kappa non-vanishing principal curvature. Then we consider this maximal operator. So for a smooth compact hypersurface with kappa non-vanishing principal curvature, Lichtman proved that the derivative of the Fourier transform of the surface measure has decay of order kappa over 2. So using this estimate, so in the paper of Rubio di Francia, he proved that.
Can you go back to the previous slide there?
Yeah, this is the
for all multi-index alpha.
Yeah, you can
right?
actually if you can prove for alpha equals to 0, you can prove it for all alpha. So using the compact support of sigma. Okay. So then in the paper of Rubio di Francia, he proved that let sigma be a smooth compact hypersurface of kappa non-vanishing principal curvature. Then the maximal function m sigma is bounded on LP if p is strictly bigger than this number 2d over d plus kappa minus 1. And if you consider sigma equals to the sphere is d minus 1, it has d minus 1 non-vanishing principal curvature, then if you put k kappa equals to d minus 1, you will get that p bigger than d over d minus 1. This recovers the result of Stein. Okay, so this is about linear maximal functions. Now we will move to bilinear and later multilinear analog of maximal functions. So the bilinear spherical averages on sphere is defined by this definition, and we take supremum over all these averages. So the study of bilinear spherical maximal function was initiated in the paper of Geba, Greenleaf, Yosevich, Falson, and Sawyer, and later Varinovo, Grafakos, Honjik, and Oliveira. They studied boundedness, and then Heo, Hong, and Yang, they improved the previous results. However, the optimal result was not there for bilinear spherical maximal function. Very recently, Jiong and Sangyuk Lee, they proved the optimal result for bilinear spherical maximal function in dimension d greater equals to 2. So in order to state the result, I will consider this set P with a subset of the unit square such that x plus y is less than this number. Then for dimension d greater equals to 2, they proved that for PQR satisfying the Holder relation, the bilinear spherical maximal function maps LP times LQ to LR if and only if 1 upon P, 1 upon Q belongs to this set P, except these endpoints when either P is 1 or Q is 1. At these points, basically, they proved weak type estimates. And what they used the idea, they used a very clever argument of slicing technique. Basically, you can slice this sphere S2D minus 1 into a d-dimensional ball and a d-1 dimensional sphere. Then you can dominate this bilinear spherical maximal function by product of Hardy-Littlewood maximal function and the linear spherical maximal function. Then using the boundedness of these classical operators, you can prove this result. However, the slicing argument does not work in dimension 1. So in dimension 1, very recently in 2022, Zhu and Michael Christ, they proved this estimate that the bilinear circular maximal function maps LP times LQ to LR for PQ strictly bigger than 2 and satisfying Holder relation. And in a different paper of Dosidis and Ramos, they proved that if you take either P equals to 2 or Q equals to 2 or both, then strong time estimate cannot be held. But can one prove restricted weak type estimates? That was not known until our work with Ankit Bhojak, Surjit Singh Chaudhary, and Saurabh Srivastava. So we proved that the bilinear circular maximal function maps the bilinear circular maximal function satisfies restricted weak type estimates. This means restricted weak type means our input functions are only characteristic functions. So this is for bilinear circular maximal function. Now we'll go back to the result of Cheong and Sangyuk Lee. So they proved here you look at their region. So this set P. So this line x plus y equals to 2d minus 1 by d. This line is not there in their boundedness result. So however, for dimension d greater equals to 3, they have restricted weak type estimates on that line segment x plus y equals to 2d minus 1 over d. But in dimension 2, boundedness at this line segment was not there. So in the same paper, we have proved this result. So okay, so for dimension 2, this is the convex hull, where in this open convex hull and the horizontal and vertical line, the boundedness was proved by Unijiang and Sang-Uk Lee. But in this line segment, half comma 1 to 1 comma half, in dimension 2, we have proved restricted weak type estimates. So this is the result, that if P1, P2 between 1 and 2, then we have this restricted weak type estimate for M2S3. And in dimension 1, as you can see that this vertical and horizontal line segment, 0 comma half to half comma half, and the vertical line. On these two line segment, in dimension 1, we have proved restricted weak type estimates. So now almost everything is known about bilinear spherical maximal function. One can also consider multilinear spherical maximal function when m is greater or equals to 3. And this is the definition of multilinear spherical maximal function. So in the same paper of Unijiang and Sang-Uk Lee, they proved that for m greater or equals to 3 and taking P1, P2, Pm all greater than 1, satisfying the Holder relation, the multilinear spherical maximal function maps LP1 times LP2 times LPM to LP if P is strictly bigger than this number. And dimension is greater or equals to 2. So in the dimension 1 case was not there. So later, Josidis and Ramos, they proved LP estimate for multilinear spherical maximal function in dimension 1. Sorry.
No, somebody came. So somebody came looking for.
Okay, sir. I am not writing there the region, I mean the convex hull where they have proved estimates because it is little messy. However, they have proved optimal result except the boundary points. And on the boundary points, we have the boundary points, strong type estimate cannot be proved, but we have proved restricted weak type estimates on the boundary points. This is in the same paper with Ankit Bhojok, Surjit Singh Chaudhary, Saurav Srivastava. Okay, now this is about spherical maximal function, bilinear and multilinear. I want to define maximal function on some different hypersurfaces. So we want to consider this hypersurface first, S of A1, A2, which is given by this generating function, mod y power A1 plus mod z power A2 equals to 1. So for the spherical maximal function, for example, bilinear spherical maximal function and multilinear spherical maximal function, the sphere is, I mean, it is symmetric and it has non-vanishing Gaussian curvature. And also, for example, the bilinear, I mean, the S2D minus 1, for any point y comma z belongs to this sphere, it is also written by that mod y square plus mod z square equals to 1. That is the generating function for sphere S2D minus 1. And it has non-vanishing Gaussian curvature. So if we consider a hypersurface which has vanishing curvature condition, can we prove boundedness of the maximal function defined on it? So this is one example of such hypersurfaces. So here, observe that if we take A1 equals to
can you repeat this point? What did you say?
Okay. So for sphere SMD minus 1, it has non-zero Gaussian curvature. So therefore, I mean, so it has nice property, non-vanishing Gaussian curvature, and also the sphere can be written as like the point y1, y2, ym belongs to the sphere. Then these points are, I mean, they have this relation mod y square, mod y1 square plus mod y2 square dot plus mod ym square equals to 1. This is the generating function for sphere. And it has non-vanishing Gaussian curvature. So if we consider a hypersurface which has vanishing curvature condition, I mean, the Gaussian curvature may vanish at some points. So then if we consider a maximal function on that, bilinear or multilinear maximal function on those hypersurface, what can we prove? So this is one example of such hypersurface. And if we, in particular case, if we take, let's say A1 equals to 2 and A2 is this number 2L, where L is greater or equals to 2 some integer. Then this is the generating function. And observe that the Gaussian curvature of this hypersurface vanishes at these points theta comma 0 with mod theta equals to 1. Now if we consider the maximal function on this hypersurface, so let's see. So this is our bilinear maximal function defined on this hypersurface, and we want to study the boundedness, LP boundedness of this operator. So let P be the set which we define for bilinear spherical maximal function. Then we define a new set P of A1, A2 given by the points x, y belongs to P such that x is less than this number and y is less than this number. Where this plus means R plus is basically maximum of R comma 0. And note that from this definition of this set P A1, A2, if both A1, A2 less equals to D, then this set P A1, A2 is nothing but P intersection with the right open right open square, unit square 0, 1. 1 is, I mean, this line, the top line and the right line. X equals to 1 and y equals to 1. That line, those two line segment is missing. So, okay. So this is one observation that how this set P A1, A2, A1, A2 behaves. Now this is our result. So let D greater equals to 2 and A1, A2 are real numbers greater equals to 1, and take PQ between 1 and infinity, satisfying the polar relation. Then this bilinear maximal function maps LP times LQ to LR if 1 upon P, 1 upon Q belongs to this set P A1, A2. And this is sharp in the sense that if we take 1 upon P, 1 upon Q belongs to outside of the closure of this set, then the operator cannot be bounded from LP cross LQ to LR. So except from the boundary points, we have a sharp result. And this set basically when A1, A2 is strictly bigger than the dimension D, the set P A1, A2 looks like this. Okay, and so to prove this result, we again used the slicing argument. So because this hypersurface here is written by this function mod y power A1 plus mod z power A2 equals to 1. So because of this information, even if the curvature is vanishing, because of this information, we can use slicing argument. So, and we also consider the multilinear analog of this operator. But for multilinear case, m greater equals to 3, we don't have a sharp result. Okay, now for sphere and this hypersurface, we have this generating function for the hypersurface. Now, if we only know that a hypersurface with some curvature condition, but we don't know anything about the generating function, then what can we prove about the maximal function defined on those hypersurfaces? So we want to consider more general hypersurface. So let sigma be a compact smooth hypersurface contained inside the unit ball with kappa non-vanishing principal curvature. Then we consider this multilinear average defined by this. D sigma is the normalized surface measure on sigma. And then we consider both the local maximal function, where we take supremum over the compact interval 1, 2, and the full maximal function also, where we take supremum over all the positive real numbers. Now we want to study LP boundedness of these operators, especially the boundedness of the global maximal function. Now when AM is 2 and sigma be a compact smooth hypersurface with at least D plus 3 non-vanishing principal curvature, then Chen, Grafakos, Honzik, and Slavikova, they proved that this maximal function maps L2 times L2 to L1. And this result very recently, in fact, in November last year, was improved by Borges, Foster, and O. They proved that the L2 L1 estimate holds if the hypersurface has at least D plus 2 non-vanishing principal curvature. And of course, we can interpolate with those trivial estimates, like taking one function out with sup norm, then it will be a linear maximal function. Then we can interpolate with L2 L1. Then we can prove estimates, but we cannot prove estimate when this target space is a non-Banach space. Means some LP1 times LP2 to LP when P is less than 1. Those estimates are not known for this operator, even if M is 2. Now we want to consider the multilinear analog of this operator, which we defined here, M sigma. So for multilinear case, we proved that if the hypersurface sigma has at least, it has kappa non-vanishing principal curvature, which is strictly bigger than M minus 1 into D plus 1, then this operator maps L2 times dot L2 to L2 over M. Now, in the case of spherical maximal function, for example, bilinear spherical maximal function and multilinear spherical maximal function, the same technique works. Like the slicing argument works for bilinear maximal function, bilinear spherical, and also multilinear spherical maximal function. But here, in the case of general hypersurface, the proof which was given by Chen, Grafakos, Ho, Hanjik, that proof does not, that technique does not extend to multilinear case when m greater equals to 3, because the target space is non-Banach space here, because 2 over m is less than 1 when m greater equals to 3. So their technique only works when this target space is Banach space. So in this work, we have given a uniform proof for all multilinear case m greater equals to 2. And in order to, and here also observe that when m is 2, this kappa is strictly bigger than D plus 1, which means kappa is greater equals to D plus 2, which recovers the result of this improved result of Borges, Foster, and O. Their technique also same as Grafakos, Ho, and Hanjik. So their technique also does not extend to multilinear case. Okay, so now in order to prove this this estimate, we first prove for the local maximal function. So this is our theorem for local maximal function. So let S is strictly bigger than this number m minus 1 into D over 2 plus half m greater equals to 2, and sigma be supported in a unit ball, and it satisfies this decay property that D sigma hat has decay of order S. Then the local maximal function satisfies this estimate. Now note that when the sigma is a compact smooth hypersurface with kappa non-vanishing principal curvature, then this order decay S is nothing but kappa over 2. This is due to the Littmann's result, which we stated in the case of multilinear maximal function. So here, if we put then S equals to kappa over 2, then these two will cancel out. So basically we'll get kappa strictly bigger than m minus 1 into D plus 1, which matches with our main theorem. So first we'll prove this estimate first for the local maximal function, and then we'll proceed to global maximal function. Now in order to prove that, first we'll prove this lemma. So let m greater equals to 2 and TMF.
Kalachand,
Yes.
This sigma is the Ostrom measure of the compact hypersurface, or is different from that thing?
No, it is, the surface measure on this hypersurface.
So yeah, that is okay. That's
Yes.
okay.
Okay, so in order to study boundedness of the local maximal function, first we'll consider this M-linear Fourier multiplier operator. So TMF is defined by this, where M is called the Fourier multiplier symbol. And suppose that there is a constant C such that this Fourier multiplier has decay property, like it decays like 1 plus mod I to the power minus S for some positive number S. And the Fourier multiplier is supported in this annulus of radius 2 to the power j. Then it satisfies this, it is bounded from L2 times L2 to L2 with this constant 2 to the power minus j into S minus this number. So we'll first prove this lemma. Then we will move to the local maximal function. So in order to prove that, we introduce this Littlewood-Perry decomposition. We'll use this decomposition later also. So let psi be a Schwarz class function on RMD satisfying this psi hat equals to 1 on this annulus 1 to 2, and it vanishes outside of the annulus half to 4. And psi j we define by scaling, and phi is the identity function minus the sum of all those psi j's. Now see, we have assumed in this lemma that the Fourier multiplier symbol M, support of this is contained inside the annulus of radius 2 to the power j. So using the support condition, we can write this Fourier multiplier operator TMF as psi j convolved with TMF because of the support property. Now, in order to prove L2 estimate, we just consider its L2 norm, and then first apply Felder's inequality. Then we will apply first a change of variable with respect to the x variable, and then we compute the x integral first here. Then the psi j will be disappear. But in order to do the change of variable, we will get this constant 2 to the power j into m minus 1 into d, and we will end up with L2 norm of TMF on RMD. Now we can apply Plancherel theorem for TMF. So we have assumed that the Fourier multiplier M has decay of order minus S, has decay of order S, and it is, the support of M is contained inside the annulus of a radius to the power j. Therefore, we have this estimate using Plancherel theorem. So this is L2 times L2 to L2 estimate for TMF. Now we need to prove estimate for the local maximal function. So first, using the Littlewood-Perry decomposition, we can dominate the local maximal function by sum of all these m log sigma j, where sigma j is defined by the surface measure sigma convolved with psi j, and sigma 0 is nothing but psi convolved with phi. And it is worth noting that m log sigma naught, it is bounded pointwisely by product of RD Littlewood maximal function. Therefore, we don't need to worry about this m log sigma naught. We only need to prove estimate for m log sigma j when j is greater or equals to 1. And in order to prove that, so we'll just recall what is the definition of m log sigma j. So m log sigma j, f is defined by supremum where t from 1 to 2, and then mod of a sigma j f. A sigma j is the Fourier multiplier operator. You can associate this with the Fourier multiplier operator Tm, where m is nothing but the sigma j hat. Okay, and by the definition of sigma j, you see that the support of sigma j hat is contained inside this annulus 2 to the power j minus 2 to 2 to the power j plus 2, and therefore all those xi I, because xi is nothing but xi1 comma xi2 up to xim, therefore all those xi I will be dominated by some constant 2 to the power j, and there will be at least one I such that that mod ii has lower bound to the power j minus 2. And here t is basically 1 to 2. So t is finite. Okay, now in order to prove by estimate for m log sigma, we need to basically prove this lemma. So let s m comma d be a number defined by s minus m minus 1 into d over 2 minus half. Then we have this estimate. Now for the moment, if we assume this estimate, this lemma, then we can prove estimate for this local maximal function. How? Because if we assume this lemma 2, then you see L2 over m norm of m log sigma is dominated by sum over j, L2 norm of these operators. Then using this lemma, we have this decay and L2 norm of Fi's. Since by our assumption that s is strictly bigger than this number, therefore s m comma d is a positive number. So we can sum over j, and the theorem for local maximal function is proved. So it remains to prove lemma 2. And in order to do that, we need to define some new notations. So we'll define some alpha dimensional measures. So let mu be a positive Borel measure on RD, and alpha is some number which is positive and less equals to D. Then mu is said to be alpha dimensional if there exists a positive constant C such that measure of a ball of radius r and centered at x0 is dominated by some fixed constant C and r to the power alpha, and this is uniform with respect to all the radius r and the point x0. Then we call this Borel measure mu to be alpha dimensional, and then we can define this notation mu alpha by supremum over x0 belongs to Rd and r greater than 0, r power minus alpha, and then measure of mu of this ball. Since this above inequality is uniform with respect to the points and radius, therefore this will be just constant mu alpha. Now we also know that we can linearize this supremum over t by a measurable
Mu
function.
alpha is, did you say that mu alpha is constant or which bounded by
No,
constant?
mu alpha is not constant. That the bracket mu alpha, this symbol.
Bounded by constant, right?
Yeah. Okay. We can also linearize the supremum over t by a measurable function t from Rd to the compact interval 1 to 2. Then by using this linearization, we can define the d-dimensional measure mu. So here I am saying I am talking about alpha dimensional measure, but in our case we need actually alpha to be d-dimensional. So the d-dimensional measure mu is defined by this equation. So from here, actually, from the right hand integral, you can see that mu is d-dimensional. Okay, now using this definition of mu, it reduces to the fact that the LP norm of the operator m log sigma with respect to dx is equivalent to LP norm with respect to the measure mu by this identity, first identity. Now, so basically, in order to prove, so here, in order to prove LP estimate of the local maximal function, it is enough to compute LP estimate of m sigma with respect to the measure d mu x comma t, and also we'll assume, I mean in the proof we will assume that sigma has compact support. So therefore, we don't even we don't need to consider all the alpha dimensional measure mu. We just need to consider that the measure mu is given by this omega, which is some non-negative measurable function, and dx dt. So which you can call weighted measure. So using the support property of Fourier, Fourier multiplier, we can just restrict our consideration of alpha dimensional measure to this weighted measure omega dx dt. Then it is given in the paper of Herimko, Sanguk Lee, and Seuko that this lemma was given for dimension d equals to 4, but without any difficulty one can prove it for any dimension d and any alpha dimensional measure alpha. So it was proved that for any positive number p and alpha less equals to d plus 1 and omega belongs to this capital omega alpha, which is weighted measure as we defined here. Then for a function f in LP of Rd plus 1, which Fourier support is a subset of a d plus 1 dimensional ball of radius lambda, then this weighted measure LP weighted norm is dominated by these constants and the LP norm with respect to the Lebesgue measure dx dt. So first we said that the sup norm of a sigma, which is basically LP norm of the local maximal function, can be reduced to just taking LP norm of a sigma with respect to the measure d mu. Then we can also replace this d mu by this weighted measure omega dx dt, and then this by this lemma it says that the weighted measure also can be dominated by this constant and just Lebesgue measure dx dt. So we'll use this lemma in our proof. Okay, so now, so in order to prove lemma 2, which was the main lemma, we need to first prove a small lemma here. So let R be a number given by 1 plus 4 times diameter of support of sigma. Actually, here we have assumed that sigma is contained inside the unit ball. So therefore, it is just a finite number, maybe 5 or 6. Then we consider this function kj of x comma t, which is given by this. So this function is nothing but the kernel of the Fourier multiplier operator a sigma j. Okay. Then we claim that if we take mod x greater or equals to this number r and t is less equals to 2, then this kernel behaves very nicely. So this kj x comma t is dominated by 2 to the power minus jn into 1 plus mod x power minus n, where n is any positive number. So we'll see the proof of it. So here, so by using Fubini's theorem and change of variable, we can write kj x comma t by this. Now look at this function x dot j minus t into y dot j, and look at their gradient. Grad j of this function x dot j minus t into y dot j. Look, y comes from this hypersurface sigma, which is contained inside the unit ball. So mod y is less equals to 1. T is also less equals to 2. So therefore, this is a finite number, and we are considering mod x to be greater or equals to r. Therefore, so we can see that modulus of this grad j of this function is greater or equals to mod x by 2 when mod x is greater or equals to r. Therefore, using iterated integration by parts formula, we have this this inequality. Now we can take L to be large enough such that it is greater or equals to md plus twice of n. Then we have this estimate. Now, since mod of kj of x comma t is dominated by this function 1 plus mod x to the power minus n and this decay to the power minus jn, when mod x greater or equals to r, the operator corresponding to this kernel will be dominated by product of Hardy-Littleton maximal function, right? So therefore, so we need to estimate this norm L2 over M norm of this. Now we can split this integral into two pieces, like one integral over the ball of radius r and other is the complement of the ball of radius r. Now for the complement of ball of radius r, we have seen that the kernel behaves very nicely, and this operator can be dominated by product of Hardy-Littleton maximal function. Therefore, the right hand side, this is the boundedness holds, the required estimate holds. Now we only need to worry about this case when the norm is taken over the ball of radius r. Okay. Now, in order to do that, in order to prove estimate for this first operator, first component here, we'll define the auxiliary operator A sigma j tilde, which is defined by this. Here, m xi comma tau is nothing but given by this integral, where rho is a smooth function, which is identically 1 on the interval 1 to 2, and it is vanishes outside of half to 4. And r is, as defined earlier, 1 plus 4 times the diameter of support of sigma. Now, we denote this curly f to be the space-time Fourier transform. Then if we consider the difference between A sigma j, our original operator, and this auxiliary operator A sigma j tilde, and which we denote by R sigma j, then you see that the space-time Fourier support of R sigma j, it is not its support is basically outside, supports lie outside of this ball d plus 1 dimensional ball of radius m into 2 to the power j plus 1. This can be seen from this definition of A sigma j tilde, because here we have, tau is supported in a ball of radius r into 2 to the power j. And we know the support of psi j hat. So therefore, this R sigma j has nice decay property also. Actually, the kernel of R sigma j has this property, which is again we can prove it by using integration bypass formula. So I'm not going to prove this lemma, but using this lemma, so we can see that this operator R sigma j, it is dominated by product of Hardy-Littleton maximal function. Then we can prove L2, L2, L2 to L2 over M estimate. Now what remains is A sigma j tilde. Now to deal with A sigma j tilde, we first look at the Fourier transform of A sigma j, and the Fourier transform in X of A sigma j is nothing but this. Then look at d sigma j hat. We know that support of d sigma j hat is contained in this annulus of radius 2 to the power j, and t is between 1 and 2. So this implies that xi1 is belongs to the ball of radius m into 2 to the power j plus 1. Therefore, the space-time Fourier transform of A sigma j hat, its support, it contains inside this d plus 1 dimensional ball of radius m into 2 to the power j plus 1. Okay. So now we can invoke the lemma which we proved earlier. So the lemma weighted measure, which I call it weighted measure. First we'll so we need to estimate this norm, right? Now we first apply Holder's inequality, then we will have this constant r power this number, and you see r is here a fixed number, so we can just ignore r here. Then we have L2 norm of this operator. Now using this lemma, which we prove that the weighted norm is basically L2 weighted norm is basically dominated by some constant into the L2 norm with respect to the measure dx dt. using those alpha dimensional measure. So we'll get this constant to the power j by 2 and this L2 norm over this RD times the interval 1 to 2. Okay. Now, what is this A sigma j tilde? So using Young's inequality with respect to t variable, the L2 norm can be dominated by L2 norm of A sigma j, because A sigma j tilde is nothing but A sigma j convolved with phi, some smooth function. Now, for A sigma j, we know that this sigma hat has decay property of order S, and its support of sigma j hat is contained inside the annulus of radius 2 to the power j. So then using lemma 1, which we proved very earlier for the operator Tm, which is same as the operator A sigma j, we have this estimate. Now we'll combine this equation 11 and equation 10. Then we have that L2 norm of the operator is dominated by this constant and L2 product of L2 norm of the function Fi's. And since this number is positive, so this completes the proof for local maximal function. Now, how to proceed from local to global maximal function? So recall that the global maximal function is given by this definition. Now we'll define this little decomposition on RD, which is given by this identity, where pk's denote the kth little Pelly projection, and I is called the identity operator. Then using this little Pelly decomposition, we can decompose these functions into these pieces here. So first term will be mu from 1 to m, this p less than k, f mu, and the second term is with p. So p k less equals to, this is the notation for the summation n from 1 to infinity p k plus n, and the intermediate all the combinations of this product. And here this Sm is the symmetric group of m elements, 1 to m. Then we consider, corresponding to these pieces, we consider this operator A alpha comma tau comma k. This is given by the supremum t from 1 to 2, and then this. And A m comma tau comma k is given by this definition. Now here, note that if we just prove estimate of this A alpha tau comma k for the identity element tau, identity element of Sm, then for other tau, the proof will be similar, because it is just a combination of permutation combination of functions. Whether I take function here, this side, or here, this side, on the right hand side. So we can take tau to be the identity element of the group Sm. Okay, now we need to consider a new operator Mn, which is given by supremum over k, all the integers, and then supremum over t from 1 to 2, and this. And a new operator GNQ, which is basically we have replaced the sup norm by the small LQ norm here. Then from here, this decomposition, you see that the global maximal function is basically dominated by a constant multiple of sum of all these operators A alpha tau comma k plus this operator Mn, and sum over n belongs to all the natural number. Therefore, we need to prove L2 to L2 over m estimate for this operator sup over k A alpha k and the operator Mn. And we'll prove it using induction hypothesis. We'll use induction on the linearity, M. We'll use induction on M. So first we will prove it for m equals to 2. So for m equals to 2 and when alpha is equals to 1, we have this lemma that this A alpha k is dominated by product of Hardy-Little maximal function and the maximal function m sigma, which is given by this definition. Now, see that if we have this lemma, then we know this Hardy-Little maximal function is bounded on L2, and also this m sigma operator for m equals to 2. So by our assumption that kappa is bigger than this number, which is d plus 1, so which is strictly bigger than 1, therefore kappa over 2 will be strictly bigger than half. Then we know from Rubio-Francis result that is a linear maximal function m sigma, that m sigma is bounded on L2 if its Fourier, I mean, the decay of Fourier transform of this measure sigma is strictly bigger than half. And from this condition, therefore, this m sigma will be bounded on L2 and Hardy-Little maximal function is bounded on L2. So we will get L2, L2 to L1 estimate if we have this lemma. Now, proof of this lemma is not very difficult. So see that supremum t from 1 to 2 and supremum over y belongs to sigma is dominated by the Hardy-Little maximal function. It follows from this the definition of this little Pelly projection operator. So here phi is a nice function. So therefore, modulus of this function will be dominated by this integral, and from here we can get Hardy-Little maximal function. So therefore, this lemma holds. Now this is for m equals to 2 and alpha equals to 1. Now when alpha equals to 2, we have even a nice situation. Like when alpha is 2, this operator A alpha k is dominated by product of two Hardy-Little maximal functions. And the proof follows from in the same way. Now the remaining case is this. Like when m is 2, we need to prove this estimate. Then the m equals to 2 will be, that case will be proved. Now if we, for example, for the time being, if we just assume this lemma, decay lemma, then the m equals to 2 case will be proved. Because the operator mn is a smaller operator than gqn, and for gqn we have this lemma. Then we will get L2 to L2 over m estimate for mn when m is 2. And for all the operators A alpha k here, because when alpha is 2, A alpha k is dominated by product of Hardy-Little maximal function. And when alpha is 1, we have this. And from here also we get L2 to L1 estimate. So m equals to 2 case will be proved. If we can just prove this lemma. Now we will use induction hypothesis that we assume that the operator, the n linear operator when n is 2, 3 up to m minus 1, this operator satisfies L2 to L2 over n estimate. Then we will prove it for n equals to m. So when n is m, n equals to m, look at this lemma that this operator A alpha k is dominated by product of alpha product of Hardy-Little maximal function and the second operator. This is a m minus alpha linear operator defined on the same hypersurface sigma. Now, by the induction hypothesis, we have assumed that when n is, this capital N is up to m minus 1, so it satisfies this L2 to L2 over n estimate. Therefore, this operator, this the right hand side, this m minus alpha linear operator defined on sigma, this will satisfy L2 to L2 over m minus alpha estimate. And also this product of Hardy-Little maximal function, these are also bounded on L2. So for A alpha k operator, we will have the desired estimate, which is L2 to L2 over m estimate. Now what remains to prove is this lemma, which I call it decay lemma. So, okay, in order to prove that, first we will apply a scaling argument. So using this scaling, this L2 over M norm of this operator is nothing but 2 to the power minus k m d over 2 and then m log sigma. Then this, observe that if we take q equals to 2 over m, then L2 over m norm of the GQN, this is nothing but sum over k belongs to Z, then this constant, and then L2 over m norm of m sigma log. Now we can use lemma 2, which is we proved for m log sigma j. Now using that lemma, we have the first inequality here. Okay. Then again we will apply scaling argument to just get back this Littlewood-Pelly projection operator, that p ni plus k fi. But in order to do that, we will get this constant 2 to the power dk over m, which will be cancelled out with 2 to the power minus kd. Therefore, we have the summation over k 2 to the power minus this constant, and then product of this Littlewood-Pelly projection operator. Now, in order to sum over k, we need to apply again Hölder's inequality. Then we get this. Then applying Littlewood-Pelly theory, we get L2 norm of the functions with this decay, and by the definition that this number delta of n, m, comma d is a positive number, so we can sum over n, so which will prove the boundedness of the global maximal function. So yes, so I think this is all.
Yeah, thank you very much for an interesting lecture. Are there some questions?
I can ask one question if you.
Yeah.
Yes.
But the thing is, this curvature, the thing kappa, that
Yes.
only comes where to give the estimate of this so-called surface measure of. The thing is, you have not used anywhere these geometric properties, right? Except for this sigma at xi has some bound.
Yes, only the decay property we need.
So if only that for that decay property you have, but the thing geometry you have not explored, right?
Yeah, not explored. Yes. Maybe with some other properties we can prove some better result also. Better in the sense that, for example, the condition on kappa bigger than m minus 1 into d plus 1, that is not sharp. So there are examples like if I consider in the case of bilinear maximal function, if I consider the hypersurface sigma to be S3 times S3. S3 is the sphere in R4. Then it is bounded from L2 to L1, but the principal curvature, number of principal curvature is 3 here, which is less than the number m minus 1 into d plus 1. So therefore, with some extra properties, along with the non-vanishing principal curvature, one can prove better estimates.
Mm-hmm. Yes. Yes. Thanks. I don't have more questions.
Are there some more questions from the audience? Yeah, if there are no more questions, then let's thank Kalachand once again. Thank you very much.
Thanks.